Back to our linear scheme so far. We have solved this transport equation analytically and numerically, and we saw there were some problems with the, or some things we have to keep in mind with the numerical solution based on finite differences. And these problems were if the transport velocity, let's have one more look at the equation itself. Here we have the equation. And A is the transport velocity, and keep in mind, we need this later. This is the factor between before the derivative with respect to u. Yeah. So and this we interpret as a velocity. And if this velocity times delta t is the size of the time step, and velocity times time step, that's a space. Sorry, that's has the dimension of space, yeah, of a length, divided by delta x, which also has the dimension of a length. So this is a dimensionless number. And if this dimensionless number is bigger than 1, then there's instability. It can also happen with other operators, other derivatives, but there's always it's always the same. If this dimensionless number that you form is bigger than something or smaller than something, then you may have instability. We can avoid the instability completely if we choose A times delta t. I just see that I should replace that with a delta, not with a d. Yeah. So I fix my slides now, otherwise it will never happen. And you should you will get the corrected slides after my after the tutorial. Yeah, okay. So sorry about that. Yes, so this dimensionless number, if this is less than 1, there will be numerical diffusion. If it's exactly 1, we actually get the exact solution for this case. But if A is dependent on, for instance, the position, which may happen, then this is not to achieve on the whole grid. Yeah, so keep in mind that this is not a solution for everything. We cannot say that this dimensionless number we choose this one and then everything is fine. But we sometimes are forced to make it smaller than or equal to 1. You know, there are other schemes, and the problems, the numerical diffusion problem becomes less prominent when we reduce the grid size. Yeah, this approximation here gets better and better. The approximation of the derivative gets better and better when delta x is getting smaller. This is actually not completely true due to round-off errors. So if it's too small, then there may be round-off problems, but this is a different story. Now let's look into a somewhat more complicated problem, and this is the Inviscid-Burgers equation. Looks very similar, but now we don't have an A, a constant velocity in front, but we have u itself. The function that we are looking for itself is a factor. So this makes this equation nonlinear because it contains a product of the function and its derivative. this makes it a nonlinear problem. It's a somewhat nice nonlinearity, but not as nice as one might wish for. And one of the reasons why this is important is that it contains the same type of nonlinearity as the Navier-Stokes equations in fluid flow. And actually, it might be a good idea when you have a short look at the Navier-Stokes equations. Yeah? I'm back on the ClayMath website. You find this when you follow the link to the claymath.org, which I have linked in my document here, this one. There's a description of all these Millennium Prize problems, and in particular, there's a description of the Navier-Stokes problem. And please have a short look at the Burgers equation here. And now let's look at the Navier-Stokes equations in n dimensions, n maybe 2 or 3. Actually, it can be defined in higher dimensions as well, but we are happy with 2 and 3, or everybody would be happy with 2 or 3. And you see, it looks very, very similar. The left-hand side looks very similar. The only thing is that U is a vector field in this case, and you sum up over all components of the vector field components times its derivative. But it's exactly the same type of nonlinearity that we have in the Burgers equation. Now, that's one of the reasons why the Burgers equation is interesting. On the right-hand side, the full Burgers equation. So what I show you here is the inverted Burgers equation. You can add a second derivative term, then it's the full Burgers equation. And the full Burgers equation exactly has this term here, which shows up also in the Navier-Stokes equations. P and F, these are external pressures and forces. You don't have to worry about that. Yeah, so I hope this is enough as a motivation. And the most important message is you can discretize this using the same method that we used before, yeah, as the in order to take a derivative. But you can rewrite the same equation in this form. Yeah, so I told you we can derive this from the continuity equation that we have derived. Let me show the continuity equation again. Oh, sorry. No, I thought I had it in the. Here's the continuity equation for one dimension. And if we set J, we say that J equals U squared over 2, then we get exactly the same equation by the chain rule for taking derivatives. Yeah, so we can also write this equation in this form. Yeah? Because if you derive that, you get 2 times U times the inner derivative, which would be this term. Yeah, and the 2's cancel out. So it's exactly the same equation. You can write this in 2 representations, and you can then discretize it. And this makes a huge difference. Before we look at the numerical schemes, we do let me tell you something about the solutions. We're a little bit short of time, so one can show what I will tell you here. One can derive this with the method of characteristics. If there should be time enough, which I don't expect, but maybe we can do it and come back to it in the tutorials. If there should be time enough, I can explain the same thing with the method of characteristics, but I think we can also get some intuition what happens using our experience that we have with this transport equation. Yeah, have a look at this equation again. I told you, I hope you see the cursor. The factor in this equation in front of this spatial derivative can be regarded as a transport velocity. Now, the transport velocity is proportional. In this case, it's exactly the value of u. And I will show you only, u could also be negative. I will show you solutions only where u is positive. Yeah, so we assume that that our flows are traveling from left to the right. If u is negative, these solutions are perfectly possible as well. Then the flow is moving from right to the left, and we have to take this into account. I want to simplify it a little bit. Therefore, let's assume that u is a positive function. Yeah, so the transport velocity is now a function of u. Yeah, and let me do the following. Here I come up with a scheme. Let's look at this at the same initial value problem. We solve the same problem as before. Yeah, we have the same initial condition. I also use periodic boundary conditions, but we have the same initial condition. And we have the same initial conditions. Yeah, so we start at a time equal to 0. We start with this pulse here. Okay. Now, of course, I said the now we have a positive or non-negative solution. So, for instance, here we have almost 0 as the velocity, and the function itself is also it's the function, but it's also the transport velocity of the function. Yeah, so that's a little bit crazy, but that's how nonlinear problems work. It's that means where the amplitude, so where the value of u is small, there will be a very small very slow transport to the right. Yeah, where it's big, there will be a fast transport to the right. You know, that means the mass that is located here in this area, that will have a faster transport velocity than the mass that is located in this area. Yeah, and the mass in this area will have a slower transport velocity than the mass in this area. And maybe you have an idea what will happen then. Yeah, so overall, we guess because we have a positive u, that means we have a transport from left to the right. Yeah, assuming that the function is nowhere less than 0. Yeah, but you see, matter in this region here is slower than matter in this region, which means that the matter in this region will at some point overtake this matter here. And what we see here, and that can also be nicely illustrated by the method of characteristic, is that that the matter here overtakes or is trying to overtake the matter here, and a shock is forming. Yeah, so there is shock formation, depends on the initial conditions. Yeah. If the function were decreasing, so we can look at other initial conditions later. If there are other initial conditions, then no shock will form. I wanted to play around with that with you in the tutorials, and maybe you have an idea what you can do. Yes, so the classical solution breaks down where the shock is, and yes, so the this matter wants to go as fast as possible to this side, and then it meets the slower matter here. So, and this is why a shock is building up. I hope you get the intuition at least. And this means that there is a region where you have a jump of the value of u. Yeah? So it jumps from 0, or it jumps from a high velocity here, yeah, where this matter gathers in a way, yeah, because the fast matter is overtaking the slow matter here, and then it falls rapidly down to 0. This is called a shock, and this is a natural thing that should occur depending on the initial conditions. There are initial conditions, and based on this intuition, I wanted to play around a little bit in the tutorials with it. There are initial conditions where you don't have a shock. Okay, so and now we have to choose. We can either discretize this version, that is the so-called conservative form of the Burgers equation, or we discretize it in this form. No? What would we do there? Here in this equation, we update. This is very, very similar to what we have done before. So we update the values between 0 and 1. Okay, I see I have different initial conditions. So I ignore, I fill the space with, I ignore the value at the boundaries. So this would be basically, I set the values at the boundaries to 0. Maybe I should have done this, but we can play with the boundaries conditions as well. Yeah, so all inner points are updated with 0.5 times sigma times the discretization of this term. Yeah, so that means u. Yeah, so we take u at this position. Sorry, this is the non-conservative. Ignore this for the moment. UN is U non-conservative. Yeah, we take UN at a position and multiply it with the difference of the value at the position and the left neighbor. Yeah, left neighbor, because we also need an upwind scheme because we have a positive velocity. If we had a negative velocity, we should use the scheme in the different direction. Yeah? Then we would have to take a forward derivative because information is coming from the right. So this is the naive implementation in a way, yeah, by this equation. Now we discretize this equation. What does this mean? This means that we update. That's the other scheme. Now, this is the non-conservative scheme, and this is the conservative scheme where we have the same equation but in a different formulation. Yeah, then what is this? How can we discretize it? We take the finite difference of this value, yeah, but of u squared over 2, not the finite difference of u. Yes, so we just update with 0.5 times the finite difference of u squared. Yeah, so that's an approximation of the space derivative of u squared over 2. Now, and in order to compare these schemes, I do both at the same time, yeah? in the same loop. So the idea is the same again. I also compute sigma for reasons that I will tell you a little later. And let's start the simulation. Yeah, okay. I said capital T is 2, so we are integrated from 0 to 0. So in the beginning, in this, both our schemes should yield the same results. So because nothing has happened, we didn't have propagation. Now let's move a little bit ahead. Let's say let's do a few time steps and look what happens if t equals 0.1. And then you see things as expected start to move a little bit to the right. 0.1 is a little small. Let's go to 0.5. Yeah, and you see this effect, and you also see the first effect that this that the curve is getting steeper here. Yeah, so let's zoom in. You see, it's steepening up here a bit. And what is the reason for that? Yeah, it's because here the matter moves faster than here. So the matter tries to overtake the matter here in a way. Yeah? So it's getting steepened up, and the tail on the left is getting flatter. And we can also understand that because this part here, the matter here, is slower than the matter here. Yeah, so that's, I think, quite reasonable. And note that the conservative scheme and the non-conservative scheme, so both integration schemes are giving us almost exactly the same solution. Yeah? So I think we have to, when we zoom in much more, yeah, then we see there are some slight differences, but only tiny differences. So it looks as if you could be very happy with both schemes. Yeah, let's proceed. Now, time is flying. Let's go to t equals 1. And still, yeah, so the effect is getting more pronounced. You see, it's getting steeper. The differences are getting a little bit more pronounced, but not overly so. Yeah? But the tendency is clear. Yeah? We see that a shock begins to form. It's getting steeper and steeper, and we almost get a kind of jump while the tail to the left is getting wider. Okay, so why not move a little bit further? T equals 2, and okay, still looks quite okay. And we see so here, so the tail is getting even wider, and the shock is getting more pronounced. Yeah, so here we definitely see the formation of a shock front, where we have a jump from a high velocity to a small velocity. And actually, you can you can actually compute how fast the velocity, how fast the shock front moves. There's an analytical solution based on the method of characteristics. Yeah, looks quite nice here. Tiny differences on the left side. So the left tail looks perfect. Formation of a shock front, but the shock is a little bit faster here for the conservative scheme. That's something we should keep in mind. Yeah, let's look at it. Okay, now let's increase the time again. 5. Okay, and now things are getting a little bit crazy. Yeah? Our conservative scheme, now the shock front of the conservative scheme begins to propagate much faster. while here it seems to have stalled here. So for the non-conservative scheme, for the naive propagation, we see here it stops at around 7 point something, while the shock front in the conservative scheme proceeds. Yeah, and this is getting more and more pronounced when we increase the time to 15, and we see now that there's we can see something systematically. So then the shock front is moving considerably slower for the non-conservative scheme than for the conservative scheme. Now it's at 8. Let's go to t equals 25. Yeah, and it's getting slower and slower. Propagation is much slower. While the shock front, and this is much closer to the truth, the shock front proceeds according to the non-conservative in the conservative scheme, and you can actually compute the scheme, the shock velocity, and you will find that it's basically the difference between here and here, the difference of concentrations. Yeah? So the shock velocity should be something like 0.3. Yeah? So when I go a little bit ahead, let's say by 1 to 26. Here I'm at 12 point something. Let's see where the shock front is. So it's around 13, and it should be 13.3. I would expect would the shock be in the next. Okay, it's 13.2. Now it's getting a little bit smaller. Yeah, but the shock keeps on proceeding, and it's slowing down in this non-conservative scheme. Let me see whether one of you has an idea. You are encouraged again to answer by chat. Let me see if one of you has an idea why this happens. Why do you think? So this scheme seems to be better than this one. When we discretize this, it's better than when we discretize this. Any idea? See if I see something in the chat here. Now the problem is that in this scheme you multiply with the velocity, and if it's small, very small, it's very hard to get matter inside, because you let's say it's 0, let's say it's exactly 0. Then it's impossible to get matter into this interval. Yeah, yeah, because you multiply it with 0, so you update with 0 again and again. Huh? So when you are at exactly 0, it's impossible to get out of this situation. Huh? While the conservative, you see here in the conservative scheme, you get actually an update from the left. Yeah? So matter can actually, it's not multiplied with this exact 0. So this is why this shock front is halting in this in the non-conservative scheme. So, okay. Yeah, I waited a few seconds to make sure that there are no questions so far. I don't see. I don't see questions. Yeah. So next thing is let's so what one lesson we should learn from that, and if you don't look into it in detail, yes, so you, in the continuum limit, as partial differential equations, this equation is exactly the same equation like this. But when you make your discretization, the discretized equations are different. Yeah. So if we make a naive discretization, we get this update scheme. If we make a discretization which takes into account this flow velocity, this stream proportional to this flow proportional to u squared y. So we take the numerical derivative of this function instead of the numerical derivative of this function and this function. Sorry, of u times the numerical derivative of that. Yeah. For the exact derivatives are exactly the same, but the discretizations are different. And this leads to completely different behavior. Now, let's assume we don't know anything, or we don't know too much. We don't have an intuition that actually this should be a developing shock front. We didn't do our characteristic method, which would confirm that there is a moving shock front. By the way, you see this is coming closer and closer, sorry. To a jump. There is a bit of numerical diffusion. Why is there a bit of numerical diffusion? Why, yeah, because we cannot guarantee that sigma is now, yeah, in a way, sigma is u times, it's a transport velocity times dt over dx. We don't see it in our update scheme, yeah, because it's basically this is what we had called sigma. So the meaning of sigma has changed slightly, but if we increase the number of grid points, now let's assume that we want to solve the problem at on 20,000 grid points. Yeah, it's not much of a problem. Just takes longer, as we see. Okay, that's a little bit too long. Maybe I should show it the other way around. Okay, sorry. So I have to restart the kernel. We make it the other way around. Okay, so I set the number of data, the grid size to 200. And you see, when I decrease the grid size, the front will be smoother. Yeah? This is an effect of numerical diffusion. Actually, it might be desirable because the complete Burgers equation contains a diffusion term as well, and you can, in a way, compensate for that. But just to here for comparison, so this is for a grid size of 200. You see, it's a bit smooth, and for a grid size of 2000. You can immediately see that this is much steeper. And the smaller I make the grid, the steeper you will the shock front will become. Yeah. So here we already have a very pronounced shock front. Okay. It's called conservative equation. Why is it called conservative equation? Because it's conserving something. We have the continuity equation. So every mass that leaves an interval or the continuity, we don't lose mass from the system. Yeah, every piece of mass, when we have a concentration, every atom will be transported to the right sooner or later. No atom gets lost. And actually one can show that that means that the integral over these curves, or the integral under these curves, should be constant. And we see that this is clearly not the case for the green. So the area under the green curve is certainly smaller than the area under the blue curve. And the area under the orange curve, that might be that this is the area under the blue curve. Keep in mind that, and by the way, on the right-hand side of the front, right of the shock or of the mistaken shock front here, we still get pretty good agreement between the conservative and the non-conservative scheme. Yeah, so you see, I have to zoom in pretty much in order to see differences. But the problem is the shock front. So what I just told you, that the mass should be conserved, that can be proved easily. I assume periodic boundary conditions. So every piece of mass that leaves this the system here and re-enters here. This is a period boundary condition, periodic boundary condition. So the concentration at L at this point will be exactly the same as the concentration at zero. Yeah, think of it of a loop, as a loop. The same would hold if there is no left and right boundary at all. For instance, if this extends to infinity and to minus infinity, and this here extends to plus infinity, and we assume that the mass, that the concentration approaches zero for x to plus or minus infinity, I should say. Yeah. Then the total mass, so the integral under this curve is a constant. It's conserved. Yeah? It's a constant in time. Omega is the domain. So either plus infinity to minus infinity or U to L. Yeah. How can we see that this is a constant? Yeah, it's a consequence of the equation. Sorry, I see one mistake. A consequence of the Burgers equation. Yeah, because if we take the time derivative of m, this means we'd have to take the time derivative, and we do this only for the periodic boundary conditions here. We take the time derivative of this integral, and this, if used well-behaved, which we assume, we can take this time derivative into the integral, and what we will get from here is the partial derivative with respect to time of of u. Yeah, that's here. But now we know that we know the Burgers equation. The Burgers equation says that the time derivative of u is minus d over dx u squared, the half of u squared. Yeah. So this is the error that I made, or actually I made two small errors. I should write this as a partial derivative. Partial, and I forgot the minus sign. Minus, and also minus sign. Yeah, so we use the Burgers equation. So this equals to minus the derivative of u squared half. And now we have an integral over a derivative with respect to x. But we know integration with respect to x inverts the differentiation with respect to x. So we can make use of our okay, one more. Sorry, let's see, let's check. We can make use of a fundamental theorem of differential of calculus, that the integral over a derivative is the indefinite integral evaluated at the boundaries. Yeah, so let's see. Here we have a plus sign. Yeah, so this. I hope this was the last error. This should be a plus. Yeah, yeah. This is elementary calculus. So we have this is ut at position L squared minus UTL squared plus UT at 0 squared, but we have periodic boundary conditions. So everything, no matter, which means nothing is left. Every piece of matter that runs out of the that crosses the right boundary re-enters the system over the left boundary. You know, so this is periodicity in U, and of course then we also have periodicity in U squared. Yeah, so this value is the same as this value, and so these sum up to 0. Yeah, this means that that the time derivative of the mass, of the total mass, the integral, is a constant. And actually we can put this to a numerical test. Oh, let's do it. This contains exactly the same thing, and what I print in the end is first the total mass under the integral and for the initial condition. Then we compute the total mass by summing up all the values under the. Actually, it should have been I should write times dt delta x times dx. Only then it's the integral, or an estimate of the integral. Yeah, we do that, and we see that the total mass at time t was 1.772 and so on, and we see we are, as we can see with the naked eyes. Yes, so this integral will certainly be smaller than the blue one. We have lost more than half of the mass following the non-conservative scheme. Yeah, the reason is this factor 0. Everything which is coming from the left will be eaten up in a way. No, it's lost because it's multiplied with this almost exact 0. The conservative scheme, the integral under the orange curve, however, is very, very close to the exact integral. Yeah? You see, we have only a tiny error. These are round of errors. Yeah? So the lesson we should take, we should learn: if there's a conservation law, then please make use of it. Yeah, so okay, I'm almost finished in time. I think that's not all what we can say about the system, and I would encourage you to play a little bit with the system, and we will play together with this system after the break. But I think that's it for the moment, and we will discuss it in 10 minutes. Yeah, so let's have a 10-minute break and meet again at 10 past 3.